Hello again. So I'm back with the summary of polynomials. This was a problem that we did. We used Descartes' rules of signs to figure out how many real positive zeros there were, real negative zeros, imaginary zeros, and it turned out that there was one real positive zero and two negative with the zero factor theorem. And actually what we did was we used the zero factor theorem to figure out one of the zeros, which happened to be 2, so we rewrote it as x minus 2. And then we used synthetic, we did synthetic division first. Found a factor x plus 3, x plus 6, but it was x squared plus 9x plus 18. Factored into that, plus the x minus 2 root that we already had. And basically we wrote this into this. And this is a lot more pleasant to graph. Actually, it's extremely more pleasant to graph. And I'll go ahead and show you really quickly. It's a cubic function. It's a positive function, because the leading coefficient is positive, and it's odd because one arrow is going to go one way and one arrow is going to go the other way, but anytime it's positive, the right arrow is always going to go up. If it's even and it's positive, then both arrows are going to go up. If it's even and it's negative, then both arrows go down. I digress from that. Here we go. So I don't know exactly what this graph looks like, and I guess if you wanted the most perfect graph, you'd have to sit there and plot it on tables, or you could use your graphing calculator. It doesn't have to be perfect. The understanding has to be solid, which is why I have reservations sometimes about the graphing calculator. So you have a 0 and 2 at -3 and at -6. And here we go. Since it's odd, it's going to end up going this way. Since it's positive and it's odd, it's going to end up going this way, which means it starts here. Not a perfect graph, like I said, but here we go. It's going to look something like this. Now, here's something very interesting about this. The domain of this problem, because we haven't really discussed that in a while, is from -infinity to infinity. I can plug in any x value I'd like to my heart's content. The range for this value is how high and how low it goes. Well, it goes all the way to the bottom and it goes all the way up, so it's -infinity to infinity. There's points called relative maximums and relative minimums. A relative maximum is just where the maximum tends to be on a particular interval, and the relative minimum is where it happens to be a minimum at a particular interval. Then there's called extreme maximums, which are the biggest maximums. This one goes on forever. And there are extreme minimums, which go down forever. And there are a few ways to find relative maximum and minimums, and I'm not going to go ahead and discuss that actually, because I don't think that this is the best way to do it. What you can do is use a graphing calculator, and you can kind of locate it, using, I forgot what the function is. I don't always use graphing calculators. Or you can plot a table and make an approximation. But what I would suggest, and you have to have a lot more math in order to do this, is use applications of derivatives, derivation, in order to figure it out. And maybe, if I'm ambitious, I'll keep going with these lessons, etc. But basically, I look at the rate of a change of a problem, and I take the first derivative and second derivative tests, and basically I can find points of inflection. That's basically where something goes from concave down to concave up. And then also critical points, interesting points where the rate of change is 0 at that particular point. And so on and so forth. It finds relative maximums and relative minimums. It's a lot cooler of a way, and not only that, it's an accurate way to do it. At this point, though, you just kind of have to guess or use a graphing calculator, which in my idea takes out the fun, but that's how I teach it too. I take it out and I'm like, okay, let's go, and let's locate, the maximum, let's locate the minimum. And then students ask the question, is there a way to do this by hand? I'm like, yeah, take calculus. And it's actually not difficult at all, to be honest. It's just under that, mystical name, so it's got to be difficult, but it's not really. So that's an example of this function that we drew. I want to do one more really quickly. Again, this is just a hypothetical. I'm going to just draw it out and see what happens. So let's say I have like f of x equals x to the 4th plus something, 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 something. I don't know what it's going to be. Now in this case, it's got 4 zeros, two real negative zeros, 2 positive real zeros. The domain is from negative infinity to infinity. The range is not, though. The range is bounded in the bottom. Whatever the lowest possible point of this graph is, and it doesn't go all the way down, it's probably this point right here, and you'd have to calculate that as, well, this point, all the way to infinity for the range. So that's pretty cool, and that's where applications of the graphing calculator actually work out very well. But this would happen to be the minimum, and in order to do that, you'd have to find the extreme minimum, relative maximum. Well, you don't have to find all those points. All you'd actually have to do to find the range is that. But if you also wanted to find this relative maximum and this relative minimum, etc., that'd be pretty cool too. So that's my summary of polynomials. It's actually quite applicable and quite cool. And in retrospect, it's very broad and general. And you learn a little bit at a time, and then your skills keep getting built up as you take more and more math classes. I mean, when I first took this, I didn't know anything about calculus when I was first doing these things because, you know, I didn't take that class. I took, you know, class in algebra first about that. But yeah, if you keep going with your math, etc., you can learn different applications using polynomials. That's my summary of sorts. I don't really have anything else to say on this. That's it. Have a good day. Goodbye.